Imagine a civilization a trillion years from now, not human, perhaps, but intelligent, curious, equipped with telescopes that make the James Webb Space Telescope look like a glass bead, computers that could simulate the entire physical history of our current universe in an afternoon. A civilization at least as capable as ours, possibly far more so, that has spent its entire existence studying the sky. They look out into their universe. They see one galaxy. Not one galaxy among billions. Not one galaxy that is observable from their position, while many more lie beyond reach. One galaxy, total. The only one within their cosmic horizon. A single, massive elliptical structure, the remnant of a billion-year-old merger between two older spiral galaxies. They observe this galaxy for millions of years. They measure its stars, its dark matter, its chemical composition, its age. And everything they measure is consistent with a universe containing exactly one galaxy. That galaxy having formed from some kind of initial conditions, and nothing else existing anywhere. They have no evidence of the Big Bang, because the cosmic microwave background radiation, the clearest relic of the Big Bang's afterglow, has been redshifted beyond any possible detection threshold by the expansion of space. They have no evidence of or galaxies, because all other galaxies have long since crossed the cosmological event horizon and are permanently out of causal contact. They have no evidence of cosmic expansion, because expansion does not pull on local gravitational structures, and the ONI structure remaining within their horizon is gravitationally bound and locally static. They would conclude, with enormous rigor and great confidence, that they live in a single galaxy universe. That the universe is old but finite and small, that it always was this way. They would be wrong. And they would have no way of ever knowing that they were wrong, because all the evidence that they were wrong, the cosmic microwave background, the receding galaxies, the large-scale structure of the universe, has passed beyond the boundary of what physics permits them to observe, permanently, not because their instruments were inadequate, because the physical laws of their universe had closed those windows forever. That civilization is not fictional, it is us, separated by time. In approximately 100 billion years, only the merged Milky Way Andromeda galaxy will remain within our cosmological event horizon. What those future observers will be unable to see is not hidden by technology. It is hidden by the accelerating expansion of the universe, which is right now, tonight, permanently removing galaxies from the set of things that any observer in our location see and ever know about. The answer to why no telescope can see beyond the observable universe is not that we haven't built one powerful enough yet. The answer is profoundly more disturbing than that. There are two different things that people mean when they talk about the edge of the observable universe, and confusing them changes the nature of the problem entirely. The first is the particle horizon, the boundary of the region from which light has had time to reach us since the Big Bang. Right now, this is a sphere approximately 93 billion light-years in diameter. The universe is 13.8 billion years old, but because space has been expanding throughout that time, the most distant objects we can currently observe are about 46.5 billion light-years away in every direction. This boundary is the edge of what we can see today. The second is the cosmological event horizon, the boundary beyond which we will never receive new information, no matter how long we wait. This is the boundary created by dark energy, the accelerating expansion of space that is pulling distant regions away from us faster and faster. Objects beyond this horizon, currently at approximately 16 billion light-years, are already receding faster than light can travel through space toward us. Light they emit today will never reach us. The particle horizon is large and slowly growing. The cosmological event horizon is smaller, and, in terms of the number of galaxies contained within it, shrinking. The disturbing answer involves both of these boundaries. What they are physically, why neither of them can ever be crossed by any observation, no matter how advanced, and what they imply about the permanent limits of what any intelligence anywhere in our universe can ever know. This video is about three distinct and layered aspects of the observable universe boundary. The first is the physical basis for the boundary. Why the speed of light, the age of the universe, and the expansion of space together create an observational limit that is not technological but fundamental, and what the 93 billion light-year diameter of the observable universe actually represents. The second is the cosmological event horizon. Why dark energy's accelerating expansion creates a second boundary, closer than the particle horizon, from which no future information can ever reach us. And what is happening right now, as galaxies silently cross this boundary and vanish permanently from the observable universe. The third is what the boundary implies about the limits of knowledge. Why the disturbing answer to what lies beyond is not any specific physical thing, but the recognition that physics has built a wall that no amount of intelligence or technology can ever breach, and that this wall is, under current best models, closing around us in terms of the number of galaxies it contains. Running through all three. The most recent data from DAISY, the Dark Energy Spectroscopic Instrument, whose second data release in March 2025 found evidence for evolving dark energy at up to 4.2 sigma confidence depending on data combination, and what evolving dark energy means for the future trajectory of the event horizon and the long-term observable universe. By the end of this video, you will understand the difference between the particle horizon and the event horizon, why both are permanent physical limits rather than technological ones, what happens to the observable universe in the long-term future of an accelerating cosmos, and why the disturbing answer to what lies beyond the observable universe is not a specific thing but a specific category of impossibility. What is the difference between the particle horizon and the cosmological event horizon? And why does this distinction matter for understanding what kind of limit the observable universe boundary represents? If the observable universe is only 46.5 billion light-years in radius, but the universe is only 13.8 billion years old, why can we see things 46.5 billion light-years away? What is currently happening to galaxies that are receding faster than light, and what does it mean for them to permanently cross the event horizon? Why will observers in the far future see only one galaxy and be unable to detect any evidence of cosmic expansion, the Big Bang, or the existence of other galaxies? And what does the DAISY evidence for evolving dark energy change about the expected trajectory of the cosmological event horizon over the universe's future? This is not a video claiming that something dangerous or catastrophic is happening to the universe. The cosmological event horizon is not moving toward us in a way that threatens the inner solar system or any human timescale. The galaxies leaving the observable universe are doing so gradually, over billions and trillions of years. This is also not a video about the multiverse in the speculative sense. What lies beyond the observable universe may or may not include exotic parallel universes with different physical laws. The disturbing answer to why no telescope can see beyond the observable boundary is not about what specifically lies beyond. It is about the permanent nature of the boundary itself. The honest version of this story requires being precise about what permanent means in physics. The boundary is not permanent in the sense that the universe stops. It is permanent in the sense that no physical process, no clever technology, no amount of ting can transfer information across it from beyond to within, and that permanence is a consequence of the laws of physics as currently understood. Before we go further, if the idea of a universe with built-in walls that no intelligence can ever see beyond is the kind of story that pulls you in, subscribe to Galaxy Pulse. Now, back to the observable universe, and to the two different kinds of boundary that define what we can and cannot see. The particle horizon, the event horizon, and what they mean. The universe began approximately 13.8 billion years ago in the state we call the Big Bang, a condition of extraordinary density and temperature from which space, time, matter and energy emerged. Since the Big Bang, the universe has been expanding. The space between unbound objects is growing, carrying galaxies away from each other in every direction, with more distant galaxies receding faster than closer ones. Light travels at a finite speed, 300,000 kilometers per second, and has been doing so since the earliest moments of the universe. This means that an observation made today can only include light that has been traveling for up to 13.8 billion years. The age of the universe. In a static universe, this would make the observable universe 13.8 billion light-years in radius. Nothing farther away has had time to send light that reaches us today. But the universe is not static. It has been expanding throughout its entire history. The light that has been traveling for 13.8 billion years did not travel through static space. It traveled through space that was expanding around it as it moved. The Saurk E that emitted that light 13.8 billion years ago was much closer to us when it emitted the light than the light has since traveled, because space itself expanded in the meantime, carrying the source away from where it was when it emitted the light. When we account for this expansion, the source that emitted the light we are now receiving at the observable boundary, light that has been traveling for essentially the full age of the universe, is now approximately 46.5 billion light-years away from us. That is the current radius of the observable universe. Not where the source was when it emitted the light, but where it is now, after 13.8 billion years of cosmic expansion have moved it. The boundary of this sphere is the particle horizon. Everything within the particle horizon has had time, in principle, to send light that reaches us. Everything outside the particle horizon has not. The particle horizon is currently growing, because as time passes, light from ever more distant regions has had more time to reach us. But the particle horizon is not the boundary that is truly disturbing. Under the expectation of a universe expanding at a decelerating rate, the particle horizon would grow indefinitely. A decelerating expansion means that the expansion rate slows over time, giving light from more and more distant regions an ever better chance of reaching us. In 1998, two independent teams of astronomers discovered that the universe's expansion is not decelerating. It is accelerating. The expansion rate is increasing over time. Something is pushing space apart with a repulsive force that overcomes the gravitational attraction of all the matter in the universe. This something was named dark energy, and it constitutes approximately 68% of the total energy content of the universe. Accelerating expansion creates a second, more immediately significant boundary: the cosmological event horizon. In an accelerating universe, space between distant objects is expanding faster and faster. There is a specific distance at which the rate of expansion is so fast that light moving toward us from an object at that distance is, in effect, unable to make progress. Space between us and the object is expanding as fast as the light can cross it. Light emitted by an object at exactly this distance will asymptotically approach us but never arrive. The object is receding at the speed of light. This boundary, approximately 16 billion light-years away in the current universe, is the cosmological event horizon. Objects beyond this distance are receding faster than light, not because they are moving through space faster than light, but because the space between us and them is expanding so rapidly that the gap grows faster than light can traverse it. A critically important point. This does not violate special relativity. Special relativity limits the speed at which objects travel through space. It places no limit on the rate at which space itself expands. The expansion of space is not motion through space. An object being carried outward by expanding space is not breaking any speed limit. It is being moved by the changing geometry of spacetime itself. Objects beyond the cosmological event horizon are not simply very far away. They are causally disconnected from us in the future. No signal they send from this moment forward, and no signal we send from this moment forward, will ever bridge the gap between us. Something is happening tonight, while you watch this video, that is rarely discussed in popular science. Galaxies are leaving the observable universe permanently. The cosmological event horizon is at approximately 16 billion light-years. The edge of the currently observable universe, the particle horizon, is at 46.5 billion light-years. Galaxies exist throughout the region between these two boundaries, and beyond the particle horizon. All galaxies beyond the cosmological event horizon are, as of right now, in the category of things from which no new information will ever reach us. Any light they have already emitted and sent in our direction that has not yet arrived is still in transit and will eventually reach us. But any new event in those galaxies from this moment forward, any new light emitted, any signal sent, is permanently inaccessible to us. As time passes and the universe continues its accelerating expansion, the number of galaxies within our event horizon decreases. Galaxies that are currently within the event horizon are being carried outward by expansion at rates that will eventually push them over the horizon. Each crossing is permanent. The current, best estimate, is that there are approximately 2 trillion galaxies in the observable universe. Over the coming billions and trillions of years, these will cross the event horizon, one by one. By roughly 100 billion years from now, cosmological modeling indicates that only the galaxies in our local group, those gravitationally bound to the Milky Way and Andromeda, will remain within the event horizon. All others will have crossed permanently out of reach. In 100 billion years, any civilization in our location will observe one galaxy. In roughly 150 billion years or so, the cosmic microwave background, the radiation left over from the Big Bang, will have been redshifted to wavelengths so long that it falls below any possible detection threshold. The primary observational evidence for the Big Bang will effectively have vanished from the detectable universe. Cosmology, as a science, in the far future, will be permanently impossible for any civilization in our cosmic neighborhood. Not because they lack the tools, because the evidence has been removed, irreversibly, by the expansion of space. 3 things to make concrete. The first is why distant galaxies can recede faster than light without violating special relativity. Special relativity places the speed of light as the maximum speed at which information or matter can travel through space. But space itself can expand at a ny rate, because expansion is a change in the geometry of space, not motion through it. The most distant galaxies in the current observable universe are already receding from us at several times the speed of light, and this is fully consistent with general relativity. We can still observe them because the light they emitted when they were closer to us is still reaching us, even though those same galaxies are now beyond our event horizon for new emissions. To understand why this is not a violation of anything, consider an analogy. Imagine you are standing on an infinitely long rubber sheet. A friend stands 10 meters from you. The sheet begins to stretch uniformly. If the sheet stretches fast enough, your friend's position, carried outward by the sheet, moves away from you faster than you can walk. Your friend is not running. The friend is not violating any speed limit. The sheet is expanding beneath them. The same logic applies to space and galaxies. Galaxies beyond the event horizon are not moving faster than light through space. The space between us and them is expanding faster than light can traverse it. No speed limit is violated. The information limit is violated. New information cannot bridge an expanding gap that grows faster than light can cross it. The second is what physically happens to a galaxy that crosses the cosmological event horizon. Nothing happens to the galaxy. It continues to exist, to shine, to potentially harbor life. What changes is only the causal relationship between us and it. From this moment, no new information from it will ever reach us. The galaxy is as real after crossing the horizon as before. It is simply, permanently disconnected from our causal future. This is one of the most counterintuitive features of the event horizon. The crossing is catastrophic for knowledge, but invisible to the galaxy itself. An observer in that galaxy, watching us through their own telescopes, would observe something symmetric. We cross their event horizon, and no new information from us ever reaches them again. Both crossings are the same physical event, described from different perspectives. An important clarification: some light from beyond the current event horizon can still reach us. This is because light emitted in the past, when the event horizon was farther out, is still in transit toward us. The event horizon, as described, applies to LIG-HT, emitted now. Light, emitted billions of years ago, by a galaxy that has since crossed the horizon may still arrive. It was emitted when the universe was smaller, and the separation was bridgeable. This is why the particle horizon, at 46.5 billion light-years, is much larger than the event horizon, at 16 billion light-years. We can currently see light that was emitted long ago by objects that are now, for new emissions, beyond our permanent reach. The third is the distinction between the particle horizon and the event horizon in practical terms. The particle horizon tells you what you can see today. The event horizon tells you what you can ever know, including the future. Some galaxies are currently beyond the particle horizon. Their light has not yet had time to reach us, but they are within the event horizon, meaning their light will eventually arrive. Those galaxies are temporarily unobservable. Galaxies beyond the event horizon are permanently unobservable in the sense that any new events occurring in them will never reach us. The distinction can be summarized simply. The particle horizon is about the past light cone, how far back in time and space we can see. The event horizon is about the future light cone. How far forward in space and time can any information from the present ever reach us, or reach us from there? Everything described above assumes that dark energy is a cosmological constant. A fixed energy density of empty space, unchanging over time. The standard cosmological model, lambda CDM, which has described the universe's expansion history with impressive precision, makes this assumption. In April 2024, the DAISY collaboration published its first data release, showing evidence at 2.5 to 3.9 sigma significance that dark energy is not constant but may be evolving over time. In March 2025, DAISY's second data release, based on 3 years of observation and covering more than 14 million galaxies and quasars, strengthened this evidence. depending on which datasets are combined with Dacey-Baryan acoustic oscillation measurements. The significance ranges from 2.8 to 4.2 sigma, with the 4.2 sigma figure coming from the combination of Dacey-DR2 with CMB observations, weak lensing data, and supernova surveys. The Nature Astronomy editorial published alongside the results described the finding directly. The preference for evolving dark energy over a cosmological constant has increased to a 95% for 2 sigma significance in Dacey's second data release. 2 sigma approaches the 5 sigma threshold that physics conventionally uses to claim a confirmed discovery. The evidence is not yet conclusive, but it is the strongest observational evidence yet that the cosmological constant model of dark energy needs revision. A separate note of caution. Critics including George F. Stathiou of Cambridge have pointed out that the significance depends strongly on which supernova dataset is included, with some combinations giving as little as 2.5 sigma. The Dacey finding is compelling but not yet settled. If dark energy is weakening over time, as the current Dacey data's preferred interpretation suggests, the future expansion rate would eventually slow. In a universe where dark energy weakens sufficiently, the event horizon could stabilize or even expand, in truly allowing more of the universe to become permanently accessible. If dark energy is strengthening over time, the Big Rip scenario becomes possible. An expansion accelerating so dramatically that it eventually overcomes not just the gravity binding galaxy clusters together, but the electromagnetic forces binding molecules, and eventually the nuclear forces binding atoms. All structure would be torn apart in a finite time. The behavior of dark energy over time is the single most consequential unknown for the long-term future of the observable universe. It determines whether the event horizon contracts and removes galaxies permanently, stabilizes, or expands. And it is now known, with substantial confidence, to be more uncertain than the standard model described. The particle horizon and the event horizon together define what can currently be observed and what can ever be observed. The event horizon is right now removing galaxies from the permanently observable universe. And the specific trajectory of the event horizon depends on dark energy, whose behavior Dacey has shown is more uncertain than previously established. But there is a third layer to this story, and it is the most philosophically disturbing one. What actually lies beyond the observable universe, beyond both the particle horizon and the event horizon? The answer is not nothing. The universe continues beyond the observable boundary. The question is what it contains and how much of it there is. And the answer involves one of the most consequential and most poorly constrained predictions in all of modern cosmology. Cosmic inflation. What lies beyond, why we cannot know, and what inflation implies. The observable universe is not the universe. It is the portion of the universe that we can currently observe. Beyond the particle horizon, by everything we know about physics, the universe continues. The question of how much universe lies beyond the horizon connects to the theory of cosmic inflation. Inflation is the hypothesis that the very early universe, in a fraction of a second after the Big Bang, underwent an extraordinarily rapid expansion, far faster than its current expansion rate. During this inflationary period, a tiny region of space expanded by a factor of at least 10 to the power of 26, and possibly far more, in a time shorter than 10 to the power of minus 32 seconds. To put this in terms that make the scale visceral, the observable universe, all 93 billion light-years of it, would have been compressed to a volume smaller than a marble in the pre-inflationary state. Inflation stretched that marble to the scale of the observable universe in less time than it takes light to cross a single proton. Inflation was not proposed as an arbitrary hypothesis. It was proposed to explain three specific features of the observable universe that were otherwise deeply puzzling. The first is the horizon problem. The cosmic microwave background, the afterglow of the Big Bang visible in every direction, is extraordinarily uniform. The temperature varies by only about 1 part in 100,000 across the entire sky. In the St-Andrews Big Bang model without inflation, regions of the sky that are separated by more than about 2 degrees never had causal contact. They were beyond each other's particle horizons when the CMB was emitted, yet they have the same temperature. Without inflation, this requires an astonishing fine-tuning of initial conditions, with opposite regions of the universe just happening to start at exactly the same temperature, despite never having been in contact. With inflation, the solution is natural. All the matter in the currently observable universe started from a tiny, causally connected region in thermal equilibrium, and inflation stretched this region to the scale we observe. The uniformity is not a coincidence. It is the signature of the pre-inflationary causal connection. The second is the flatness problem. The geometry of the universe appears to be extremely close to flat. The curvature, if any, is far smaller than the natural Planck scale curvature. In the standard Big Bang, flatness is unstable. Small deviations from FL at geometry grow over time, meaning a flat universe in the present requires a flat geometry tuned to extraordinary precision in the early universe. Inflation naturally drives the geometry toward flatness by stretching any curvature to such a large scale th at what we observe appears flat. Just as the surface of a balloon appears flat when inflated to cosmic scale. The third is the absence of magnetic monopoles and other exotic relics that grand unified theories predict should have been produced in abundance in the hot early universe. Inflation dilutes these to negligible densities by stretching the post-inflationary volume to enormous scales. If inflation occurred, it has a specific implication for the size of the total universe relative to the observable universe. The observable universe represents the portion of the post-inflation universe from which light has had time to reach us. But inflation would have stretched the total universe to a size enormously larger than the observable portion. The ratio of the total universe's size to the observable universe's size, under typical inflationary models, is at least 10 to the power of 23, and in MA-NY models is functionally infinite. The universe beyond our horizon, in inflationary models, is not exotic. It obeys the same physical laws. It contains the same kinds of matter and energy. It has the same fundamental constants. What lies beyond the observable universe, in this view, is simply more of the same. More galaxies, more stars, more planets, more empty space, stretching for a distance that makes the observable universe look like a single grain of sand on an infinite beach. If the universe is infinite, and if the laws of physics are the same everywhere, then the same configurations of matter that exist within our observable universe repeat at sufficiently large distances. Every arrangement of particles that exists within our Hubble volume has, in an infinite universe, infinitely many copies elsewhere. This is not exotic speculation about alternate physical laws. It is simply the expected consequence of an infinite universe with finite numbers of possible quantum states per volume. The same reason that if you shuffle a deck of cards an infinite number of times, every arrangement appears infinitely often. Whether the universe is finite or infinite is not known. The observations are consistent with either. A spatially flat universe could be infinite, but it could also be finite with a scale much larger than the observable volume. The question may be permanent, undecidable, from within our observable region. The cosmological event horizon is not a technological limit, it is a physical limit. The distinction matters enormously. A technological limit is something that a sufficiently advanced civilization could, in principle, overcome with better tools. If the only reason we cannot see more of the universe were that our telescopes are not sensitive enough, a more advanced civilization could build better telescopes. A physical limit is imposed by the laws of physics in a way that no technology can circumvent. The cosmological event horizon is this kind of limit. It is a consequence of general relativity applied to a universe with accelerating expansion. No instrument, regardless of sensitivity or wavelength coverage, can detect information from an event that occurred beyond the event horizon and was directed away from us. Not because the instrument isn't good enough, because the information is not in transit toward us. The photons were never emitted in directions that could reach us. The causal structure of spacetime in an accelerating universe has separated these events from our observable region permanently. A civilization 10 billion years more advanced than us would face the same cosmological event horizon. A civilization with the ability to construct instruments spanning light years, powered by the energy of stars, using physics we cannot imagine. None of his addresses the event horizon. Because the event horizon is not about instrument capability, it is about the geometry of spacetime. The event horizon is as permanent as the speed of light. Both are consequences of general relativity. Both apply universally. This is what makes the event horizon genuinely disturbing, in a way that ordinary technological limits are not. What the cosmological event horizon creates is an epistemological situation with no parallel in the history of science. Throughout the history of scientific inquiry, limits on knowledge have turned out to be temporary. We could not see distant galaxies until we built larger telescopes. We could not detect gravitational waves until we built LIGO. We could not image the cosmos microwave background until we launched sensitive space-based detectors. Each of these limits looked permanent from within the era when they held. Each turned out to be contingent on the state of technology. The cosmological event horizon is different in kind. It is not contingent on the state of technology. It is imposed by the causal structure of spacetime in an accelerating universe, in a form derivable from Einstein's field equations. The information from beyond the event horizon is not hidden. It is absent from our causal past. It was never in transit toward us to begin with. This creates a category of question that is permanently unanswerable, not because we haven't figured it out yet, but because the laws of physics preclude the possibility of the relevant evidence ever arriving. The total size of the universe, permanently undecidable from within our observable region. The specific configurations of matter beyond our horizon, permanently unknowable. Whether the physical constants we measure here are the same everywhere beyond our horizon, permanently undetermined by any observation we can make. These are not open scientific questions in the ordinary sense, where more work and cleverer methods lead toward an answer. They are questions that are epistemologically sealed by the physics of the universe we inhabit. This is not a statement about the current limits of human science. It is a statement about the permanent limits of what any science, conducted by any intelligence, at any point in the future, can resolve. There are three frameworks for understanding what the observable universe boundary represents. The first is the pragmatic framework. The observable universe contains roughly 2 trillion galaxies and 93 billion light-years of structure. No realistic scientific program is constrained by the horizon. The boundary is relevant only on timescales and at distances that dwarf any human concern. In this framework, the event horizon is a philosophical curiosity without practical implication. The second is the information theoretic framework. The event horizon places a finite upper bound on the information accessible from our location in the universe, and this bound is decreasing over cosmological timescales. The accessible information content of our observable universe is a finite and shrinking quantity. This is a specific physical statement with consequences for the long-term thermodynamics of an accelerating universe, and it connects to the deeper question of what happens to information at event horizons generally, a question that has driven some of the most consequential theoretical physics of the past half-century, including the black hole information paradox. The third is the epistemological framework. The event horizon is the first case in the history of science where the laws of physics themselves, rather than the current state of technology, have placed a class of questions permanently outside the domain of empirical resolution. This is philosophically significant in a way that is independent of any practical implication. It means that scientific knowledge, the kind of knowledge built from observation and measurement, has a permanent boundary that is not a boundary of our limitations, but a boundary of what the universe physically allows any observer to know. All three frameworks are valid. The horizon is simultaneously irrelevant on human timescales, physically significant on cosmological timescales, and philosophically significant as the clearest known example of an absolute epistemic limit imposed by physica law. A note on the geometry of the observable universe. One of the most counterintuitive aspects of the observable universe boundary is the apparent contradiction at its core. How can we see things 46.5 billion light-years away if the universe is only 13.8 billion years old? If light travels at 300,000 km/s per second, the most distant thing we could see should be 13.8 billion light-years away. The distance light can travel in 13.8 billion years. So why is the observable universe larger than 13.8 billion light-years in radius? The answer is that we observe objects not where they are, but where they were when they emitted the light we are now receiving. And the distance between where something was and where it is now has been stretched by the expansion of space during the time light was in transit. Here is a concrete way to picture this. Imagine the early universe, about 380,000 years after the Big Bang. The universe is dense and hot. At this moment, a photon is emitted from a region of dense gas. The photon that will eventually become part of the cosmic microwave background that we detect today. At the moment of emission, that region of gas is roughly 42 million light-years from where our galaxy will eventually form. Over the next 13.8 billion years, the photon travels toward us, but the universe expands around it as it travels. The photon makes progress. It is genuinely moving through space toward us, but the space it has already crossed is expanding behind it, and new space is being created between it and the gas cloud that emitted it. By the time the photon arrives at our telescopes today, the gas cloud that emitted it has been carried by cosmic expansion to a distance of about 46 billion light-years from us. So, we are simultaneously receiving light from something that was 42 million light-years away when it emitted the light, and that is now 46 billion light-years away. The light is ancient. The source has moved. The distance we quote, 46 5 billion light-years is the current distance to the source, not the distance the photon has traveled. The photon has traveled 13.8 billion light-years through space, but the source from which it came has since been carried 46.5 billion light-years from us by the expansion of space. Both distances are simultaneously true and refer to different things. This geometry makes the observable universe boundary not a spherical wall at a fixed distance, but a sphere whose radius in terms of current source distance is set by the expansion history of the universe since the Big Bang. Different assumptions about T expansion history, different dark energy models, for example, produce slightly different values for the current radius of the observable universe. The 46.5 billion light-year figure is the consensus estimate from the standard cosmological model. It may be revised as our understanding of dark energy's time evolution improves. Let's come back to where we started. A civilization a trillion years from now, with instruments of arbitrary capability, looking out into their universe and seeing one galaxy, concluding, correctly by all available evidence, that they live in a single galaxy universe. Unable to know what we can now, because the evidence of what we know has been permanently removed from their accessible universe by the expansion of space. That civilization is not fictional. It is us, separated by time. The answer to why no telescope can see beyond the observable universe has two components. The first is conceptual. The observable universe boundary is not defined by instrument capability. It is defined by how long the universe has existed, how fast light travels, and how space has expanded in between. These three quantities set a horizon that no improvement in telescope sensitivity, aperture, wavelength coverage, or any other instrument parameter can address, because the relevant photons are simply not in transit toward us. The second is more disturbing. Even within the observable universe, there is a closer boundary, the cosmological event horizon at 16 billion light-years, from which no new information is in transit toward us and never will be. This boundary is not the limit of what we can see. It is the limit of what we can ever know from our location, not just now, but permanently. And, under the accelerating expansion of space, galaxies are crossing this boundary tonight, becoming permanently inaccessible, removing themselves from the set of things that physics permits us to learn anything new about. Both of these answers are disturbing in the same way, not because something dangerous is happening, but because the laws of physics have built walls into the fabric of the universe, and those walls enclose a finite and shrinking region, and nothing, no technology, no intelligence, no civilization however advanced, can reach beyond them. Popular science coverage of the observable universe boundary falls into consistent patterns that fail to communicate what is genuinely remarkable about the situation. The first failure is conflating the particle horizon with the cosmological event horizon. Most articles describe the observable universe as 93 billion light-years across and leave it there, without explaining that this is the particle horizon, not the event horizon. The event horizon, at approximately 16 billion light-years, is the closer and more consequential boundary, the one that describes not just what we can see now, but what we can ever know going forward. The distinction between these two boundaries is the distinction between a current limitation and a permanent one. The second failure is presenting the boundary as a technological limit. The phrasing, "no telescope has been able to see beyond it," implies that a better telescope could. No telescope can, ever, regardless of how good, because the problem is not the telescope. The problem is the causal structure of spacetime. The light from beyond the event horizon is not faint, it is absent. There is no photon in transit toward us from beyond the event horizon that more sensitivity would detect. Framing it as a technological limitation misrepresents the fundamental nature of the constraint. The third failure is not discussing what is happening right now. Galaxies are crossing the cosmological event horizon permanently tonight as you watch this. This is not a distant future event. The horizon has existed since the universe's expansion rate began to accelerate, which happened billions of years ago. The process of galaxies becoming permanently inaccessible is ongoing and continuous. Most popular coverage treats the event horizon as a future concern. It is a present one. The fourth failure is not explaining the future observer problem. The most powerful illustration of what the event horizon means is the far future scenario. A civilization with perfect instruments, looking out and seeing one galaxy, concluding they live in a single galaxy universe, unable to detect any evidence to the contrary. This thought experiment illustrates what the horizon actually does to knowledge, not just to observations. It shows that an epistemically diligent, technologically sophisticated civilization can be permanently wrong about the nature of their universe, because the relevant evidence was removed by physics before they existed. This illustration is essentially absent from popular coverage. The fifth failure is not connecting the Dacey dark energy results to the event horizon. The Dacey finding, 4.2 sigma evidence for evolving dark energy at maximum significance, is the most consequential recent measurement for the long-term behavior of the cosmological event horizon. If dark energy is weakening over time, the event horizon may stabilize or grow, eventually allowing more of the universe to become permanently accessible. If it is strengthening, the Big Rip becomes possible. The connection between Dacey dark energy measurement and the long-term boundary of the knowable universe is essentially never made in popular coverage. And the June 2026 rebuttal by Dr. Phil Weissman and colleague Hughes, including Nobel laureates Adam Rees and Brian Schmidt, confirming that cosmic acceleration remains the best supported interpretation, demonstrating that any suggestion cosmic acceleration had ended was based on calibration errors, should be understood as a confirmation that the cosmological event horizon remains a feature of our universe's physics, not an artifact we can explain away. The most important recent development for this topic is the Dacey's second data release from March 19, 2025. Dacey has been mapping the three-dimensional distribution of galaxies across cosmic history using baryon acoustic oscillations as a standard ruler. The known size of the early universe's acoustic oscillations allows the expansion history to be reconstructed from the observed distribution of galaxies across different cosmic epochs. The second data release, covering more than 14 million galaxies and quasars across 3 years of operation, found a statistically significant preference for dark energy that is n-naught constant, but is changing over time. Specifically, the data, combined with CMB observations, weak lensing, and supernova surveys, prefer a dark energy equation of state that was stronger in the past and is weakening in the present. This would imply that the acceleration of expansion may itself be decelerating. A universe where the expansion rate is still increasing, but more slowly over time than the constant dark energy model predicts. The significance ranges from 2.8 to 4.2 sigma depending on the specific dataset combination, with the headline 4.2 sigma coming from the combination of Dacey DR2 with CMB, weak lensing, and the dark energy surveys supernova sample. The Nature Astronomy editorial accompanying the results described the finding as the dark energy sector being yet more complex than we thought. and explicitly noted that the preference for evolving dark energy had strengthened from 3.9 sigma in the 2024 release to 4.2 sigma in the 2025 release. A note of caution is warranted. George F. Stathiou of Cambridge and other prominent cosmologists have pointed out that the significance depends strongly on which supernova dataset is included, with some combinations giving as little as 2.5 sigma, and that He preference could potentially reflect systematics in the supernova calibrations rather than genuine dark energy evolution. The science is not yet settled. If the Dacey result is confirmed and dark energy is weakening, the cosmological event horizon will behave differently than the constant dark energy model predicts. A weakening expansion rate means that the event horizon expands rather than contracts, potentially including more galaxies in the permanently accessible future than the standard model would allow. In an extreme scenario where dark energy eventually reaches zero, the expansion would stop accelerating, the event horizon would expand indefinitely, and, in principle, the entire universe would become observable given enough time. The June 2026 paper by Dr. Phil Weissman of the University of Southampton, co-authored by Nobel laureates Adam Rees and Brian Schmidt, published in Monthly Notices of the Royal Astronomical Society, confirmed that the accelerating expansion remains the BEST-supported interpretation of current data, by rebutting a South Korean study that had claimed deceleration. The rebuttal identified two calibration errors in the Korean team's analysis: an incorrect assumption that the age of an exploding white dwarf matches the age of its host galaxy, and a failure to apply standard mass corrections for supernova host galaxies. When properly corrected, the evidence for cosmic acceleration returned cleanly and consistently. As Weissman's team stated, the previous and well-accepted measurements were, in fact, fine, and our current understanding of the fate of the universe remains robust. The cosmological event horizon remains a feature of our universe's physics. The debate is not whether it exists, but how it will evolve as dark energy's behavior becomes clearer. The Dacey program will continue releasing data over its 5-year survey lifetime, with subsequent data releases expected in 2026 and 2027. Each release will provide tighter constraints on dark energy's time evolution, which directly constrains the future behavior of the cosmological event horizon. The Euclid Space Telescope, which began science operations in 2024, is conducting a complementary survey of galaxy distribution and will provide independent measurements of the expansion history with different systematic effects. Agreement between Dacey and Euclid would significantly strengthen the evidence for evolving dark energy. Disagreement would indicate that the Dacey preference is driven by a systematic error in one of the measurements. The Nancy Grace Roman Space Telescope, expected to begin operations around 2027, will provide a third independent measurement using multiple cosmological probes simultaneously. The combination of Dacey, Euclid, and Roman data will produce the most complete and precise measurement of dark energy's time evolution ever achieved. Whatever those measurements find will change the predicted long-term behavior of the cosmological event horizon. How many galaxies it will contain in 100 billion years, whether the future observable universe is one galaxy or potentially more, and whether far future civilization scenario, the one galaxy universe, is certain, or merely one of several possible futures. For the epistemological question, the measurement of dark energy's time evolution is the most consequential current science, precisely because it governs the permanent limits of what any future intelligence in our cosmic neighborhood can know. This is not imply a cosmological question. It is a question about the long-term informational content of the observable universe, and it is currently being answered by the most comprehensive galaxy survey ever conducted. Here is what the observable universe boundary reveals at the deepest level. For the entire history of human inquiry, the expansion of knowledge has had a particular character. We look, we measure, we formulate theories, we look further, we measure more precisely, we refine the theories. The process has no inherent end. Each generation of scientists looks further than the last, and the universe's secrets yield progressively to the methods of observation and analysis. The cosmological event horizon is the first specific, quantified instance in the history of science where this process has a known permanent termination. It is not that the universe has secrets we haven't figured out yet. That is science as usual. It is that there are specific facts about the universe, right now, tonight, that no intelligence anywhere within our observable region can ever determine, regardless of how much more time elapses, how much technology improves, or how sophisticated the analysis becomes. How many galaxies lie beyond our event horizon? Unknown and unknowable in principle, because we can never receive new information from them. What is the total size of the universe? Unknown and likely unknowable from our position, because the evidence needed to answer it lies beyond our observational access. Do the physical constants we measure here apply everywhere? Unknown and potentially unknowable, because regions where they might differ are causally disconnected from us. These are not open questions in the ordinary scientific sense. They are questions that are sealed by the physics of the universe we inhabit, and the sealing is getting tighter. Right now, tonight, galaxies are crossing the cosmological event horizon and becoming permanently inaccessible. The total accessible information content of our observable universe is decreasing, slowly, on any human timescale, but continuously and irreversibly. It is worth dwelling on exactly what is lost when a galaxy crosses the event horizon, because popular coverage consistently misrepresents this. What is lost is not the galaxy. The galaxy continues to exist, to form stars, to harbor whatever life or civilization might be there. What is lost is causality, the ability of any event in that galaxy to influence any event in ours, or vice versa. The galaxy does not disappear. It becomes an island so far away, and receding so fast, that the light bridge between us and it has been severed, not by anything that happened there, but by the relentless expansion of the space in between. This is one of the most underappreciated features of the event horizon. It is experienced asymmetrically. To us, the galaxy has crossed a threshold and vanished from our causal future. To them, if they have the physics to understand their universe, they observe us crossing their event horizon. We vanish from their causal future. Both crossings are equally real, equally permanent, and equally the result of the same expanding space. The future observers who will see only one galaxy will not be observers who failed to try hard enough. They will be observers who live in a universe where the evidence for anything beyond that galaxy was removed before they existed. By the inexorable operation of the same physics that governs the Big Bang, the formation of galaxies, and the structure of spacetime, we live in a rare moment. A moment when there is still enough of the observable universe accessible that cosmology is possible, when the cosmic microwave background is still detectable, when the recession of galaxies is still measurable, when the evidence of the Big Bang still exists within our causal reach. We are, right now, in the best observing window the universe will ever offer any intelligence in our location, and that window is closing, not quickly, but permanently. The most disturbing answer to why no telescope can see beyond the observable universe is not that the technology is inadequate. It is that the universe has built-in walls, woven into the geometry of spacetime by the same accelerating expansion that produced the one galaxy future. Those walls enclose us. They are not moving toward us fast enough to matter on human timescales, but they exist, and they are made of physics. There is one more thread connected to this story. The cosmological event horizon is one of three types of horizon that appear in modern physics. The second is the black hole event horizon, the boundary within which gravity is so strong that no information can escape. The third, and most theoretically active is the Rindler horizon, a horizon that appears for any uniformly accelerating observer, even in flat spacetime, with deep connections to the Hawking radiation of black holes and to the thermodynamics of spacetime itself. All three horizons are related through a common mathematical structure. They are surfaces in spacetime across which no causal connection exists. The discovery that the cosmological event horizon has a temperature, a Gibbons-Hawking temperature analogous to Hawking radiation from black holes, is one of the deepest connections in theoretical physics between the geometry of spacetime, thermodynamics, and the limits of knowledge. What this connection implies about the fundamental nature of the observable universe boundary, and whether the cosmological event horizon radiates information back in a way that partially preserves what crosses it, is one of the most active areas in theoretical cosmology. That is a story for another time. We started with a thought experiment, a future civilization with perfect instruments, seeing one galaxy, unable to detect evidence of the Big Bang or cosmic expansion, concluding they live in a single galaxy universe, unable to know what we know, unable to even know there was something they didn't know. The specifics of this scenario are worth dwelling on, because they are not just poetically disturbing, they are physically precise. By approximately 100 billion years from now, the local group will be the only gravitationally bound structure within our cosmological event horizon. By roughly 150 billion years, the CMB will have been redshifted below any detection threshold. The redshift happens because space is expanding. The wavelength of a photon is proportional to the scale factor of the universe, and as the universe expands by a factor of 10, CMB photons are stretched to 10 times their current wavelength, eventually falling below any instrument's range. There is no gradual fading, the CMB simply exits the detectable frequency range and is gone. Without the CMB, the primary evidence for the Big Bang is absent. The future observer cannot see the pattern of temperature fluctuations that encodes the universe's initial conditions, cannot see the acoustic peaks that confirm the hot dense early state, cannot measure the ratio of hydrogen to helium that traces back to Big Bang nucleosynthesis. The Big Bang becomes as untestable to them as it was to pre-modern astronomers, but worse, because pre-modern astronomers lacked the tools to detect the evidence. The future observer has the tools. The evidence simply does not exist within their causal reach. Without the recession of other galaxies, the future observer cannot measure cosmic expansion. There is nothing to observe receding. The one galaxy within their horizon is gravitationally bound and locally static. Hubble's law, the relationship between distance and recession velocity that tells us the universe is expanding, is impossible to verify when the only observable structure is bound and non-receding. Then, we traced the physics that makes that scenario inevitable. The particle horizon and the event horizon, the distinction between what we can observe today and what we can ever observe. The cosmological event horizon at 16 billion light-years, from Wick H, no new information will ever reach us. The 2 trillion galaxies currently within our observable universe, which will decrease toward 1 over the next hundreds of billions of years. The Daisy evidence, at up to 4.2 sigma confidence when datasets are combined, that dark energy is evolving, which changes the specific trajectory but not the existence of the bound ARI. And the June 2026 Weissman et al. Paper, confirming with Rees and Schmidt as co-authors that cosmic acceleration remains the best supported interpretation of current data, keeping the event horizon firmly in our physics. And at the end, we arrived at the disturbing answer. Not that something specific and dangerous lies beyond the horizon, but that the laws of physics have placed a wall in the fabric of spacetime, a wall made not of matter but of causal structure, and no intelligence, no matter how advanced or how long-lived, can see past it, know past it, or determine what exists beyond it. We live in the window, the one cosmological era when the observable universe is large enough, bright enough, and full enough of evidence that a science of the cosmos is possible. That window is rare, and it is finite. Whether dark energy is truly evolving over time, or whether the Daisy preference at 4.2 sigma maximum reflects systematic errors in the measurements, is not yet determined. The Euclid and Roman Space Telescope data, expected in coming years, will provide independent confirmation or contradiction. The range of 2.8 to 4.2 sigma, depending on dataset combination, reflects genuine uncertainty about whether the signal is real or a calibration artifact. The behavior of dark energy at late times, specifically whether it is weakening toward zero, stabilizing, or behaving in some more complex way, determines the quantitative trajectory of the cosmological event horizon and how many galaxies will eventually be contained within it. Whether the universe is finite or infinite in total extent is not known and may be permanently unknowable from within our observable region. Whether the physics beyond our observable region is the same as within it, whether the same physical constants and laws apply, is not known and may be permanently unknowable. And whether the cosmological event horizon, like the black hole event horizon, radiates information in some quantum mechanical sense that partially preserves what passes through it, connecting it to the Hawking radiation framework and to the information paradox, is an active area of theoretical research without experimental resolution. First, there is a categorical difference between a technological limit and a physical limit. Technology can address technological limits. Physical limits, imposed by the causal structure of spacetime, cannot be addressed by any technology. The cosmological event horizon is a physical limit, and it is important to be clear about this distinction because it determines whether more effort and cleverness can ever overcome a particular barrier. The history of science is full of temporary limits overcome by ingenuity, limits that appeared permanent but were not. The event horizon is genuinely not that kind of limit. It is derived from Einstein's field equations. It is as firm as the laws of physics themselves. A civilization that could compute the trajectory of every particle in the observable universe simultaneously would still face the same event horizon, because the horizon is not about computation. It is about causality. Second, the event horizon is not a future concern, it is a present one. Galaxies are crossing it continuously. The process of permanent information loss from the observable universe is ongoing, not hypothetical. Every night, new events in galaxies beyond the horizon occur that are permanently inaccessible to us. The specific moment when any given galaxy crossed, or will cross, the horizon depends on its distance and recession velocity, and there is no fireworks display to mark the transition. It happens silently, continuously, at the speed at which space expands. Most popular coverage treats the event horizon as a future concern relevant to far future civilizations. It is a present physical reality, as present as the expansion of space itself. Third, the far future thought experiment, a civilization seeing one galaxy and concluding they live in a single galaxy universe, is the clearest illustration of what the event horizon means for knowledge. It demonstrates that an epistemically diligent, ethnologically sophisticated civilization can be permanently wrong about the nature of their universe, because the relevant evidence has been removed by physics. Their conclusion would not be a failure of science. It would be the correct conclusion from all available evidence, evidence that had been permanently altered by the expansion of space. Their universe, from inside their event horizon, really does look like a single galaxy universe, and no observation they can make will show otherwise. This is not a thought experiment about the limits of intelligence. It is a thought experiment about the limits of what physics allows to be known, and the limits are not about intelligence. Fourth, the Dacey dark energy measurement is the most consequential current science for the long-term behavior of the observable universe, because dark energy's time evolution determines whether the event horizon contracts, stabilizes, or expands. The mesurement of dark energy is not just cosmology. It is the measurement of the permanent limits of the knowable. A universe where dark energy is weakening is a universe where the boundary is less severe, where future observers can know more about their cosmos. A universe where dark energy is static or strengthening is a universe where the boundary closes further, where future observers know less. The difference between these scenarios, measurable now in the spectra of galaxies and quasars with instruments like Dacey, determines the informational fate of the entire observable universe for all of cosmic time. Fifth, we live in a rare observational window, the era when cosmology is possible, when the Big Bang's evidence is still accessible, when the expansion of the universe is still measurable, when the full 2 trillion galaxies are still within our observable reach. This window will not last forever. From the perspective of the universe's total duration, it is already nearly closed. The science being done right now, by Dacey mapping dark energy, by JWST imaging the earliest galaxies, by the CMB experiments mapping the temperature fluctuations that encode the universe's initial conditions, is science that will be impossible for any civilization in our location in the far future, because the evidence will have been removed. The universe is providing us, right now, with the most complete record it will ever make available from our vantage point. The work being done now is cosmology at its most possible. The cosmological event horizon places a specific class of questions permanently outside the domain of empirical resolution, questions whose answers require information that will never arrive. What is the appropriate relationship between science and questions that are, in principle and by physical law, permanently unanswerable? Should these questions be treated as meaningless because they are unanswerable, or meaningful because the universe contains real answers that happen to be inaccessible to any observer? The far future civilization will be epistemically correct in their measurements and epistemically wrong in their conclusions, not because they made errors, but because the evidence was removed before they existed. Is this a situation where they can be said to lack knowledge, or is knowledge defined only relative to what is accessible within a causal domain? And what does this imply about the relationship between truth and observability? And, on the most human level, we exist in what may be the richest observational moment in the history of this corner of the universe. The evidence of the Big Bang is still accessible. 2 trillion galaxies are still within our horizon. The expansion of the universe is still measurable. How does knowing that this window is rare and finite change how you think about the work of understanding the cosmos, and what it means to live in the moment when it is still possible? If this one stayed with you, let us know which part landed hardest, the particle horizon, and why the universe can be 13.8 billion years old, but 93 billion light years in observable radius. The expansion of space, making the most ancient light arrive from he most distant place. The event horizon, and what it means that galaxies are crossing it permanently, tonight. The far future thought experiment, a civilization with perfect instruments concluding they live in a single galaxy universe, unable to know they were wrong. The Daisy 4.2 Sigma evidence for evolving dark energy, and the June 2026 Weissman et al. Confirmation that acceleration remains real, what it changes about the trajectory of the boundary. Or, the biggest reveal. The most disturbing answer is not what lies beyond, but that the laws of physics have woven permanent walls into the fabric of spacetime, and no intelligence, at any level of sophistication, can ever see past them. And, if you want more of this, real cosmology told at the level where the disturbing answers are the true answers, subscribe to Galaxy Pulse, and we will see you in the next one. Tonight, a galaxy crossed the event horizon. It did not explode, it did not change. It simply crossed a line in the geometry of spacetime, a line that means no new light it emits will ever reach us. It joined the permanent dark. Tomorrow, another will cross, and the night after. And, for every night that follows, for longer than the universe has so far existed, we live in the bright window. The one cosmological moment when the evidence is still here, when the signals are still arriving, when 2 trillion galaxies are still within reach. The window is open, for now. The Gibbons-Hawking radiation, and what it means for the event horizon. There is one more layer to the cosmological event horizon that receives almost no popular coverage, and it connects the horizon to some of the deepest theoretical physics of the past half-century. In 1977, Stephen Hawking published his famous result that black holes are not perfectly black. Through a quantum mechanical process, now called Hawking radiation, black holes emit thermal radiation at a temperature inversely proportional to their mass. This radiation is produced at the event horizon of the black hole, the surface from which no information can escape, through a process involving quantum fluctuations of the vacuum just inside and outside the horizon. The result was startling. A surface that, by classical physics, allows nothing to escape turns out, by quantum mechanics, to radiate. In the same year, Gary Gibbons and Stephen Hawking showed that cosmological event horizons have the same property. An observer in a universe with an accelerating expansion, surrounded by a cosmological event horizon, experiences a thermal bath of radiation, the Gibbons-Hawking radiation, at a temperature that depends on the horizon's distance. For our current cosmological event horizon at approximately 16 billion light-years, this temperature is fantastically small, about 10 to the power of minus 30 Kelvin. It is immeasurably cold. But it is not zero. The physical significance of this result goes beyond the negligible temperature. It connects the cosmological event horizon to a framework where event horizons in general, black hole horizons, cosmological horizons, and the Reindler horizons of accelerating G observers all share the same mathematical structure. They all have a temperature. They all have an entropy proportional to their area. They are all, in the information theoretic language of modern physics, surfaces that carry information about what has passed through them. Whether the cosmological event horizon, like the black hole event horizon, preserves information about what crosses it, whether the galaxies that disappear over the cosmological horizon are truly lost, or Whether their information is encoded in the Gibbon-S Hawking radiation they leave behind is one of the open questions at the intersection of quantum mechanics and general relativity. If the cosmological event horizon is like a black hole horizon in this deeper sense, then the information content of the galaxies that cross it is not permanently destroyed, but is encoded in the radiation they leave behind as they cross. This would not mean we can extract information about specific galaxies from the radiation. The encoding is enormously scrambled. But it would mean that the permanent information loss we have been describing is, in some deeper quantum mechanical sense, not absolute. This is an active area of theoretical research. There is no experimental resolution, but it connects the question of what happens at the cosmological event horizon to the deepest unsolved problem in theoretical physics. The information paradox, the question of what happens to information that falls into a black hole. The observable universe boundary is not just a cosmological curiosity. It is a window into some of the most fundamental physics of space, time, information, and the nature of the laws that govern our universe.